talked about this idea of charge, different things about it, likes, repel, opposites attract, all that good stuff, okay? So I thought I would bring in a couple of balloons. Everybody loves balloons. I don't know if everybody does. So these are not charged. They may have a little bit of charge on them. But if I charge them up, so I'll just charge them by rubbing them on my frizzy hair. Okay, that one is going to pop in my ear, I know it. Okay, so now you can see that, well, it didn't really, maybe there's a little bit of charge. Must do better. All right. Usually works well, but it's pretty damp down here right now. And my hair is a little bit damp. Okay. Yeah, okay, there we go. Yeah, all right. So they have a little bit of charge on them. So they're repelling one another. They're like charged, I don't know, they're probably negatively charged. They pick up a few little electrons from my hair and they get a net negative charge on them. So now we have this extra force acting on the balloons. If we look at one balloon and draw the free body diagram, you have tension in the string, mg, and then there is this force, and maybe I'll call it Fe, okay? There's an extra force acting on it that is due to this charge on the balloon. All right, so this is the force that we're going to get a handle on, looking at the magnitude of this force, and we're going to use it in all kinds of different ways. So let's take two charges, Q1 and Q2. Most of the time, charges are given the letter Q. Why, I don't know. But that's just, historically, charge is given the letter Q. A point charge is usually a lowercase q. If you have a collection of charges, it's sometimes a capital Q, okay? So let's say there are two charges, Q1 and Q2. I don't really care about the magnitude of the charges right now. And let's say that Q2 is positive and Q1 is positive as well. We know from what we talked about that there's going to be a force pair based on this. If they're both positive, that's F1 and that's F2. I can name those forces whatever I please. I'm naming them the force on one, and that's the force on two. A lot of text will cook up all kinds of fancy notation for these things, like F12, F21, R1. Okay, we'll do a little bit of that, but in the beginning, I think it's a lot simpler just to draw the picture, look at the physics. Okay, these are the same SIGN charge, and we know that they're going to repel one another. If they were opposites, they would attract. Okay, I'd still name this F1 and this F2, but they would be this way. Okay, I'm going to name the distance between these two. So this is just the distance, just call that R. Okay. Now, these forces always act on a line between the two charges. So you draw a line between any two charges, and those forces are on that line. I didn't draw the line down here, but I mean, there wouldn't be any reason for the force to be acting this way due to, okay. It's always along a line connecting to the two charges. I hope that's obvious. The magnitude of this force is called Coulombs Law, is due to Coulombs Law. Coulombs Law is F, that's the magnitude of the force, is equal to K, Q1, Q2, and I'm going to go ahead and put these in absolute value sign divided by R squared. This is an R squared or an inverse square force law. Just like gravity, even though in Physics 1, didn't do a lot if you had me over the summer. We didn't do a lot with gravity, but gravity is the same way. You have a big G, a big mass, a little mass, and then their distance squared, okay? So this is the magnitude. I don't care about the SIGN of the charges, plus or minus. Just getting rid of that, I'm just calculating the magnitude of the force. This is a force pair. These two forces, in this particular case, well, really in all cases, when you're just looking at two charges, F1 magnitude equals F2 magnitude. Okay? All right. Let's talk about this value of K. The Coulomb constant, I'll call it. That's going to give us a way to make this work out in newtons. We're going to make the force work out in newtons. The Coulomb constant, what we will use is 9 times 10 to the 9 Newton meters squared per Coulomb squared. Okay? So the meters cancel, the coulombs cancel, and you get the force in newtons. Okay, here comes Daniel. Okay? You will sometimes see this written, the more fundamental constant is called, and I'll tell you anyway right now, permittivity. It's an old-timey word of free space. It's just a name. The permittivity of free space is epsilon naught, and that's equal to 8.854 times 10 to the negative 12 Coulomb squared per Newton meter squared. Okay? This is related to this. This constant is related to this constant this way. K is equal to 1 over 4 pi epsilon naught. So sometimes in the, in the problems and so forth, you'll see 1 over 4 pi epsilon naught in the place of K. They're the same thing. Okay? This is the more fundamental value, but this is the value that we'll use for solving problems and so forth. All right. So you take the product of the charges over the square of the distance between them and multiply by K. That gives you the force in newtons. Let's see how this works. Couple of warnings about Coulomb's law. These have to be in coulombs, and this has to be in meters, obvious. Well, just make sure. It's very easy to get going, and I'm giving you charge values that are in nanocoulombs or microcoulombs or whatever. You got a question?
if these were in coulombs?
They need to be in coulombs, yes, to get the force to work out in newtons. So, very simple example. Here is a 3 microcoulomb charge. I'll put the plus there for emphasis, and a negative 5 microcoulomb charge. Okay, let's say they're separated by something simple, 0.5 meters. So 50 centimeters separates a plus 3 microcoulomb and a negative 5 microcoulomb charge. What do the forces look like? Well, these are attractive, so this would be F, I'll call it F3, and this one is F5, okay? These are still forces, they're vectors, all right? So the first thing I'm going to do is I'm going to figure out what's the magnitude of the force. I'm typically going to use this first. Then, if you're asked for a direction or something like that, you look at the picture. Okay? F3 is in the positive x direction, F5 is in the negative x direction. Okay? So let's find the magnitude of these forces. This is a force pair. This is an action-reaction force. So F3 equals F5. You guys are familiar with my notation. If I do not put the little arrow over the variable, then it's just a magnitude. It's not a direction. Okay? So this is equal to K times 3 times 10 to the negative 6. That's micro. I'm going to ignore this negative because I'm just looking at the magnitude, taking the absolute value. And then 5 times 10 to the negative 6 coulombs divided by 0.5 meters, quantity squared. Okay. So this is equal to, it's 1.5. What do you get here? Get a 5, a 1 point, something that's 3, I don't know, K. Well, let me write it out. 9 times 10 to the 9 Newton meters squared per Coulomb squared times, can somebody calculate this? This is 15, that would be 7.
I got, if I already multiplied like all three of them together, and I got 27 over 200.
Well, what happened to the 10 to the negative 6?
I multiplied all of the top together already.
Oh,
Yeah.
okay.
That's what I got.
Okay. So this is 15. I'm just going to write this out. Times 10 to the negative 12 Coulomb squared divided by 0.25 meters squared. Okay. So that's 6. That's equal to 60 times 10 to the negative 12, I guess. So that's 6. That's 5.4 times something. Can you calculate that?
So
I think.
The actual answer
Yeah.
is 0.54.
Okay. So it's 5.4. Okay, I'll just write it as 0.54 newtons. That's half a newton, roughly. Okay. So that's the magnitude of the force. If I asked you what is F3, F3 is equal to 0.54 newtons. I hat F5 is equal to 0.54 newtons with a negative I hat. Okay. There are all kinds of fancy ways to do bookkeeping where you put the negatives in here and the negatives cancel and you get a positive. Okay. I just think it's too technical. Now, there will come a time when we will have to pay attention to the SIGN of the charge when we get to potential and so forth, but not today. Coulombs law is simple. It's an inverse square law. It's how we calculate these electric forces on charge. Are there any questions on that? I'm going to do a little more complicated example, but okay. Let's see. This looks good. All right, so let's say we have three charges arranged in an equilateral triangle, or on an equilateral triangle. So here's the XY plane. Here's Q1. Here's Q2. Here's Q3. That's not too bad. I guess I better follow what I got in the notes. Okay. Plus, minus. Okay. So I'm going to make this plus 1 microcoulomb. This will be negative 2 microcoulombs. And this will be plus 2 microcoulombs. Okay. So I'm going to call this Q1, Q2, and Q3. Okay? Q1, Q2, Q3. This distance is 2 meters. 2 meters. 2 meters. So this is an equilateral triangle. Here's the question. What is the force on Q2 due to Q1 and Q3? Okay. These forces are like any other forces that you encounter, and you can add them, you can subtract them, you can multiply them, you can do all the things that you did with forces in Physics 1. When you're looking at multiple charges, you're simply adding up the forces. In the way that I do it, you may want to do it a different way, but the way that I do it is I'm going to draw a picture of the force from charge 1 and the force from charge 3 on Q2. I'm interested in the force on Q2. I realize there are other forces around. I don't care about those. I only want to look at the force on Q2. What's the force on Q2 due to Q1? What's the direction of the force? Yeah, so it's this way, right? I'm going to call that F1. Now, I could call it F12 or F21 or something fancy, but that's the force due to charge 1. That's what I'm thinking of. What direction is the force between 2 and 3 on Q2? Yes. This is an attractive force, so I'm going to call this F3. Well, these are vectors, all right? Now, all that's left is to figure out the magnitude of these two forces, and then I can do the normal thing, and that's break them into components, add the components, find the resultant. Which is larger, F1 or F3? Magnitude. I'm looking at F1 and F3. Okay, F1 arises from a 1 and a 2. F3 arises from a 2 and a 2. Yeah, F3 is going to be larger than F1, right? Okay. So let us calculate those magnitudes first. So F1 magnitude equals, I'm just going to put the numbers in, 9 times 10 to the 9 Newton meters squared per Coulomb squared. Then I have a 1 and a 2. So I have 1 times 10 to the negative 6 coulombs multiplied by 2 times 10 to the negative 6 coulombs, and all of that divided by this distance squared, 2 meters squared. Okay. So that's magnitude F1. So that's 4.5 times 10 to the negative 3, maybe? Brooke to calculate for me.
Mine's not giving it in exponent form. It's just a really good number. So after multiplying the whole entire top, it's 9 over 500.
Yeah.
And then dividing that by 4 is 0.0045 newtons.
Yeah. 4.5 times 10 to the negative 3. Okay. So that's the magnitude of F1. F2 is the same game, except now it's going to be pretty simple. Then we have 2 times 10 to the negative 6 coulombs multiplied by 2 times 10 to the negative 6 coulombs divided by 2 meters squared. And this is going to be equal to 9 times 10 to the negative 3 newtons. Okay. That's these two. I ignored the negative. I'm just looking at magnitude. Okay? So now I have to break this up into components. So I'm going to put a little x. This is getting really, here's the x-axis. Okay. I'm going to put a little coordinate system up here. All right. What is this angle? Interior angles or exterior angles of parallel lines. What is this angle? It's an equilateral triangle. What's the sum of the interior angles of a triangle?
360,
180.
180. I have not seen geometry.
Okay. That's okay. 180, this is equilateral, so what do you guess each one of these is going to be?
180 divided by 3.
Yes, which is 60. Okay. We got there finally. Okay. So that's 60 degrees, so these are parallel, and that's a line cutting across, so this is 60 degrees. This is 60 degrees. Okay. By the same argument. Okay, let's go ahead and go through this, even though I know you know how to do it, but. So we need F1x, and that's equal to 4.5 times 10 to the negative 3 newtons times the cosine of 60 degrees, if I'm looking at it right. Do you agree with that? That's F1. I'm looking for this component. Okay. F1y is equal to 4.5 times 10 to the negative 3 newtons sine 60 degrees. F3x is equal to, well, F3x is something positive. That's going to be 9 times 10 to the negative 3 newtons cosine 60 degrees. Here's where I have to be a little bit careful. F3y, F3 has a y component in the negative y direction. So F3y is negative 9 times 10 to the negative 3 newtons sine 60 degrees. Equals, equals, equals. Okay, can somebody give me a Brooke?
0.5 newtons. I have.
For cosine 60?
Yes.
0.5 newtons. Okay, I'm leaving out the I hat for a minute.
And then 0.866.
0.866 newtons. Okay, so this must be 1 newton. Are you sure?
I didn't get 1 newton for that one.
Something's wrong because I just don't think this comes out to a half.
We tried again.
Cosine 60 times 4.5.
I'm still getting 0.5.
Really?
Yeah.
Can somebody else calculate
Somebody else
this?
do it.
Cosine 60 is a half, right? So this should be like 2.25?
Times 10 to the negative 3.
Yeah.
I'm getting something different every single time and I'm putting in the same things.
Just do 4.5 times the cosine of 60. And we'll add the 10 to the negative 3. We'll tack it on.
Okay, that one works.
Yeah. And for this one, sine of 60 is,
3.89. Not, that's not 4.5, that's in minus 3 though.
what'd you get?
0.897 times 10.
Okay, 3.897, so can I say 3.9 since we're just working on the board? Okay. Oh. Okay, so this must be 4.5 times 10 to the negative 3 newtons. Huh?
I got 4.5.
Yeah. And this must be 7.8 with a negative.
Yeah.
Okay. All right. Shall I keep going? Well, now we add components. So you have a 4.5 plus 2.25, so FR, I'll call it X, that's the resultant, is F1X plus F3X, which equals 6.75. F resultant Y is equal to F1Y plus F3Y, which is equal to negative 3.9. If I did that right. Okay. Okay, well, what's the magnitude of the result? Well, we know where the resultant is anyway. It's down here somewhere. This is getting even messier. Okay, there's FR. It's down there. It's got a positive X component and a negative Y component. So, FR is equal to FRX squared plus FRY squared. Can somebody calculate that, please? Maybe about 8? I don't know. 9? Something like that.
Yeah, like 7.7 times 7 minus 3, or 7.8 times 10 minus 3.
7.8 times 10 to the negative 3 newtons. Okay. And the angle, well, lots of ways you can express this angle. I'm going to look at this one, theta R. Okay. So that's going to be theta R is equal to arctangent of negative 3.9 divided by 6.75. So that equals what? Something.
Negative 30.
Negative 30 degrees. Okay. So once you get to the point where you know what your vector magnitudes are and where they live, and you've calculated those magnitudes using Coulombs Law, it's just the same thing we did in Physics 1. Find the components, add the components, find the resultant. Okay? Are there any questions on this? Okay, so what do we got? A couple of minutes.
What chapter is this in the book?
Oh, the first one on the syllabus. It was 21 in the old book. I think it may be 22. 21, 22, something like that. What? I haven't. No, I haven't posted any homework. It's coming. Believe me.
Like
23. Okay. You sure it's 23? Maybe. I don't know.
What is it called? Coulombs Law? Like, would that
Should be electric forces or something.
be electric field? Yeah, Coulombs Law is in 22.
Yeah, 22. Okay. All right. Just give you a little thought, something to think about. Let's say you have two charges, a +1 microcoulomb and a -5 microcoulomb. And they're connected along some line. They're stable, okay? Plus and a negative. I have a wayward positive charge. I don't really care what the magnitude of the charge is. I can make it, let's say this is a +1 microcoulomb. Is there a place along this line that I can place the +1 microcoulomb such that I get 0 net force on that charge?
Sure there is.
You're sure there is? Okay, where is it?
Don't know.
Can I put it in between here somewhere? Like kind of tune it till I get 0 force? You're saying no, why not?
Well, because it doesn't equal. Unless you put it on the other side.
Yeah, what happens in between? If I put the plus in between somewhere here, I get a force this way from the 5, and I also get a force this way from the 1. No good. There's no place in between that I could place this charge and get no net force. Okay. What about over here? Well, over here I've got the +1, that would be F1 this way, and then F5 would be this way. Okay, these are vectors. Could I find a spot over there? Well, it almost looks like you could, but I'll tell you what happens on that side. The 5 will always, even though I drew the vectors as if the 1 was larger magnitude than the 5 will always win. You're farther away from the 1 and it's smaller. You cannot find a place over here where you can make these two forces cancel. This is out. We could prove that mathematically, but I hope you can see from just what we talked about with the physics that this will always win. Okay, but over here, there is a place, okay, because F1 is in this direction, F5 is in this direction, and you can find a spot over here where you can tune this, or you can play around with it, and I'll show you how to do that next time, such that these two are equal. The 5 is farther away, and you get close enough to the 1 or far enough from the 1 where you make these two forces equal in magnitude to one another. Okay, I'll see y'all next time.